So I think some of you may have heard versions of this talk before at the Fontaine conference or at Don Blasius's conference. So again, this is joint work with J-P.Wintenberger. So he gave a talk about this a couple of months ago. Maybe I can assume you all remember it and take off from there, but I'll just try to recall the notation and so on. Okay, so I'm going to start with F, a totally real field. And I'll look at an odd prime P bigger than 2, P odd prime. So let me just begin by recalling the basic setup of Iwasawa theory. So of course, I mean, there's this formal thing that if you look at the class group of F, you can also describe it as kind of pick naught of OF. It's just a formal fact, but then Iwasawa deepened this analogy by by finding some kind of deeper analogies between the theory of between the structure of class groups and known facts about Jacobians of curves, let's say, over finite fields. But instead of looking at just at F, looking at one class group, he systematically looked at a sort of sequence of class groups. So you look at F, and you look at F infinity, which is F adjoint all the pth roots of unity, p power roots. Right, so this is some kind of extension, and this has a totally real. This has some kind of ZP part of this extension, which I'll call F infinity. And then there's a small part here, which is a finite group of order dividing p minus 1, cyclic group. And for simplicity, I'll assume this is the smallest it can be given the fact that F is a totally real field. I'm going to assume just complex conjugation generates. And then this is basically built out of a sequence of extensions Fn, where Fn is basically something like F mu p to the n plus t for some constant t, and then the Galois group of this is something like z mod. Okay, it's something arbitrary z mod p to the n minus 1. Where it is an n there. Okay, so this is the situation, and now instead of looking at just at one class group, you look at the class groups of all these guys. So you look at an minus, which is the minus part under complex conjugation of the Silo P subgroup of the class group of this nth intermediate extension. Okay, and then you can look to get a kind of good analogy. Kind of a deeper analogy in this formal fact, what one can do is look at the inverse limit under the norm map of an minus, and you get an object which I by definition called A infinity minus. Sorry, not A infinity, I call it X infinity minus. Okay, and then by class field theory, this is the same as looking at the kind of maximal unramified everywhere extension, abelian P extension of F infinity, which is unramified everywhere, on which the complex conjugation here acts by minus 1, and this is just X infinity minus is just the Galois group of this extension. Yeah. And the other thing which will play a role here in this talk is there's another extension Y infinity, Galois group of an extension, where this is the maximal abelian P extension of this totally real subfield of this real subfield, ramified only at P. And one of the basic facts which we'll kind of use here is that there's a pairing from Y infinity tensor QP. Okay, maybe I'll come back to this. Okay. So all these things. So if you look at so this X infinity minus has a structure of a kind of lambda algebra, where lambda is the Iwasawa algebra, ZP double bracket T double bracket gamma. So I'll sometimes call this gamma, as it's traditionally called there. And this by sending, so you choose a generator little gamma of capital gamma, and you can sort of send it formally to gamma equal to 1 plus t, and this kind of establishes a non-canonical isomorphism, which Sayre noticed was useful in the theory, that this ZP gamma then becomes isomorphic just to the power series ring in 1. And as a piece of notation for this, I've chosen a gamma equal to gamma, and then gamma, I want to keep track of how this gamma acts on the p to the infinity roots of unity. So this is basically described by some number in ZP star, which I'm going to call u. And then 22. All right. So this is, so it's a basic theorem of Iwasawa that all these modules which I'm considering x, so x infinity minus y infinity, these are all finitely generated torsion lambda module, and then Iwasawa conjecture in analogy with Weis theory of Jacobians of curves over finite fields. He conjectured a formula for the characteristic polynomial of x infinity minus. So the main conjecture which of Iwasawa theory, that is you can attach this situation a certain principal ideal of it's called a characteristic ideal of x infinity minus, which for all practical purposes is just the characteristic polynomial more or less of gamma is generated by the characteristic polynomial of gamma acting upon x infinity minus maybe tensor cube p or something, if you want to get some finitely generated object. All right, so roughly it is this characteristic polynomial, and then the formula was that this is equal to something else. So this formally denote Wt, and this Wt is linked to zeta values. So what is Wt? Wt it is given by the form, it is given by this interpolation property. It is given by the interpolation property that when you, it's supposed to be so the Deligne-Ribet periodical function upon is equal to the Deligne-Ribet periodical function, which in turn is kind of has this property that interpolates the zeta value. So zeta fp of 1 minus n for positive integers n is given by for positive even integers n is given by product of 1 minus norm p to the n minus 1 times the classical the zeta of f 1 minus n. By theorem of Ziegel, one knows that these values are rational. So this is the interpolation property of the periodical function. Okay, so this is the main conjecture, and it was proven in a series of works by using a method kind of inaugurated by Ribet, elaborated much more later on by Mazur, Weil, and Weils. So this theory, this is very much an analogy with for those, I suppose everyone here knows the basics of Iwasawa theory, so I won't kind of go into this spiel about the analogy. Okay, so this is an analogy with the fact that the zeta function of a curve of finite field is given more or less by the characteristic polynomial of the Frobenius acting on the L-adic Tate module of the Jacobian. Okay, maybe I should say that. This is I'm going to use this analogy. So this is analogous. The fact that if you look at a curve x or a smooth projective reducible curve or a finite field, then if you look at the zeta function of, then this is given by the characteristic, the kind of determinant of 1 minus frob q to the minus s acting upon the first étale cohomology of x with some coefficients away from p, where p is a characteristic of q of fq. So this is some kind of analogy. It was conjectured in maybe an analogy with this. Okay. So now I want to think of, so this I'm going to, this one can call the primitive main conjecture, one can look at the imprimitive main conjecture. So now instead of looking at x infinity minus where you allow no ramification, you kind of choose a finite set of primes and then allow ramification above those primes. So you look at let's say q equal to some finite set of primes q1 up to qm, and for simplicity I'm going to always assume that the qi are inert in this kind of real cyclotomic ZP extension, and I'm also going to assume that, all these are not necessary, but also going to assume that norm qi is congruent to 1 mod p. And then instead of looking at x in L infinity minus the maximal unramified everywhere extension, you can allow ramification at pq. And I get a certain Galois group I'm going to call x infinity q minus. So again, I should say that these are congruent to 1 mod p. So in particular, there are no primes above p in this set. And okay, then you get this x infinity q minus, and using class field theory is very easy to describe the relative structure of x infinity q minus with respect to x infinity minus. And this is just equal to, for the gamma, so everything is a sequence of gamma modules. So this as a gamma module sequence is just equal to this. So you get this, and then the imprimitive main conjecture, of course, which is a kind of a trivial corollary of this trivial corollary of the main conjecture. Once you do this class field theory calculation, which is easy. So the imprimitive main conjecture would say that the characteristic. I haven't. Okay. So the characteristic power series of x infinity q minus as a lambda module is equal to some element of the power series ring, which has the property that w q of t, when you evaluate it at u to the s minus 1, where u is kind of linked to gamma, is just equal to zeta, the Deligne-Ribet periodic L function, product of q and q of 1 minus norm q to the 1 minus s. Right, so it's like one has to notice that there's this curious shift that this is not the kind of imprimitive. It's not the imprimitive zeta function exactly, because there's this kind of factor of 1. There's a shift of 1. There's a kind of standard thing that shows up in various places. Like for example, in Tate's account of Stark's conjecture, there's this formalism of s and t, and some primes, and this shift of 1 is kind of some well observed phenomenon. All right, so this is the imprimitive main conjecture, and it follows directly from the primitive main conjecture. But on the other hand, now one has an extension of objects, and when one looks at characteristic power series, one loses some information. So one can ask, can one kind of do something more? One can ask exactly what kind of extension this is of gamma modules. So there again, guided by an analogy with Iwasawa's kind of analogy, one can try to make an analogy with what is known for Jacobians. This time not just for Jacobians of curves over finite fields, but all kinds of Jacobians over any field. Okay, so can one ask for more? Can one sort of know more in this context? So one can ask for kind of what kind of extension you get, right? So let me recall. For example, if you are given a smooth projective curve over any field, k, and you're given some points p, q, which are k rational, you can make out of this curve a curve with nodal singularity, which I'll call x p q. You get by pinching p and q together to make a nodal singularity, and then this has its own Jacobian, and this has its own Jacobian, and this has its own Jacobian, and then there's an exact sequence. Right? And it's a well-known fact. You can ask for the class of this extension. The class of this extension somehow gives you an element of of x1 of j by gm, which is pic naught of j, which is j, right? And then the class of this extension is just p minus q. This is the class of this degree 0 divisor in the Jacobian. Right? So this is a standard fact. So one can ask, is there an analogous formula here? I'm going to restrict attention to m equal to 2. M equal to 1, you don't get any extra things. M equal to 2 is an interesting enough case. Okay, so now first of all you have to make analogues of all these things. So I want to define something analogous. I want to ask for a fact analogous to this fact, and that's for the imprimatur main conjecture. What kind of extension this is? All right, so I have to define. I have to define some analog of p minus. Maybe I should also say that there's also a kind of related fact which is more relevant, which is gotten by just looking at the Tate modules of all these things. So, for example, let's assume k is. Again, one doesn't really need to assume anything about k, but okay. So z. So if we look at the Tate modules of all these things, if I L away from the characteristics, okay, L away from the characteristic of k, so then you get something like. And then you can ask for the class of this extension, and this is a certain element of H1 of H1 of gk with values inside Hom of the extreme objects, Hom the linear homomorphisms of and this by the way pairing is just equal to this, and then the class of this just turns out under the Kummer map to be the class of this point p minus q in the Jacobian, right? So this class is just the class of p minus q again. So it's just an L-adic incarnation of this more geometric fact. Okay, so this is kind of more the kind of stuff which I want to do because we are faced with the situation of Galois modules. Okay, so I have to define some analog of the way pairing, and I have to define some analog of the degree 0 divisor. So the way pairing, this is a classical, this is a result of Iwasawa, but there's at least after tensoring with QP, there's a perfect gamma equivariant pairing between these two Galois groups. Okay. So this is an analog of the way pairing which one can try to exploit here. And so one has to now define the analog of the degree 0 divisor p minus q. And for that, what you can do is you can look at so what is the analog? So we have an analog of the way pairing. What is the analog of p minus q? So you look at maybe I'm going to call this this entire group y infinity prime. So you look at the max. So you look at Galois. Okay, so what you look at is you look at this Galois group. You look at this Galois group y infinity prime, which is not in the abelian group. Then you go modulo its close commutator subgroup, which is just gamma minus 1 of y infinity. So this is just the Galois group of the maximal abelian p extension of f unramified outside p. And now, of course, because q is away from p, q1, q2, and I'm restricting attention to 2 primes. One can define certain Frobenius elements here. For each q, for q1, q2, you can define Frobenius qi. And sitting inside this, so this is some kind of analog of the pic. But if you want to look at degree 0, you have to look at something like y infinity modulo gamma minus 1 y infinity. And this sits inside some kind of exact sequence. This goes to Zp. This is the kind of f infinity or f extension, Galois group of that. And so I want to define with respect to Frobenius qi, I want to define a certain submodule of this degree 0 part. So I do the obvious thing. I look at mq. I look at the degree 0 submodule over Zp spanned by the Frobenius of Qi. Right, so I have two elements in this Galois group. I can look at the Zp linear combination and look at only those which map to 0 here. Right, so this by definition is the degree 0 part. Okay, so now this I claim is some kind of good analog of this situation of this geometric situation. So, for example, let me have this exact thing. Okay. So one can prove some kind of one can prove some propositions which tell you why this could be a good analog of this geometric situation. For example, one can prove the following, that MQ is finite. So one can also observe it's a cyclic module. So MQ degree 0, it's a cyclic. So the question is whether it's finite or not. But so MQ is finite if and only if 0 goes to, so you look at the sequence I started with and tensor it with QP, if and only if splits as a sequence of the gamma modules. And somehow one is thinking that MQ captures the property of this extension, so it does capture one property, it captures whether it splits or not. I mean, it splits up to isogeny if and only if the class is, if this Frobenius module has finite order. And one can have a slight refinement that, in fact, the original exact sequence without tensoring. Okay, let me make a further assumption here. I'm going to assume for simplicity that mu p infinity of fv is equal to 1 for v dividing p. Okay, under that assumption, one can in fact show that MQ is trivial. I should have given that exact sequence a name, so let me give it a name. It's trivial if and only if the exact sequence itself splits. So at least that one has some kind of and one can also make a more precise thing that one can look at exactly how much it doesn't split, and it's exactly related to the order of MQ. So there one can sort of, it's something which plays a pretty close role to what P minus Q plays in the theory of extensions of Jacobians. Okay, and so now once one has this proposition, in fact one sees an immediate connection with the Leopoldt conjecture. Of course, this is not historically the way we went about it. We were trying to find a criterion for the Leopoldt conjecture which could be attacked using kind of modular forms. Okay. But you can reformulate it in this way. So as a corollary of this proposition, so let me first say the Leopoldt conjecture for f and p it is a statement that has several equivalent statements, which are in fact formally equivalent. The way I'm going to state them is that f infinity of f is a unique Zp extension of f. Another way of saying it in this notation I've introduced is that the group y infinity over gamma minus 1 y infinity is finite, which is basically a rephrasing of this first condition. And what else? I mean, the more traditional, of course, the way Leopoldt stated the conjecture is that if you look at the units of f and look at those which are congruent to 1 modulo all the places above p, Yeah, and then you can regard this global points, these things, inside the 1 units of the local units. So these are the 1 units of the places above P. Then if you look at this kind of map and you look at the closure of, if you look at the closure of the image of this under the p-adic topology, then the ZP rank, by which I mean the ZP rank of the free part of this finitely generated ZP module, this should equal to the degree of f minus 1. Okay. So these are all kind of equivalent statements. This we go from this to this by class field theory. Okay, so now as a corollary of this proposition, one has a criterion for the Leopoldt conjecture in terms of something which apparently looks different. Which is the first part of the proposition, which gives a condition for finiteness of MQ. Corollary to the proposition is that Leopoldt conjecture is true if and only if. Okay, I should have called this exact sequence something. If and only if. I'll call this star QP and the star ZP. And also it's indexed by Q maybe, because okay, if and only if star QP is splits, maybe I should have called it also QQP. For all Q. And of course, one doesn't need to prove it for all Q. One just has to prove it for some Weil and you have to choose some Qi which satisfies some very weak looking properties, and that will be enough. I mean, if you fix a Q1, if you can manage to prove it for one Q2 in any one prime in a set of density 1 prime set of primes, it will be enough. Right? But still, I mean, it's no easier, and it's still not so easy to prove even weaker statements. Okay. Okay, so how do you deduce the corollary from the proposition? The proof is just by the Cherenkov density theorem and Burnside's theorem or something, some basic facts about about groups, P groups. You can show that the MQs span the finitely generated ZP module right? And so if all of these things spanning sets all have a finite order, this finitely generated ZP module is going to have finite order. So okay, so this is and how do you prove the proposition? I think Jean-Pierre probably can give the proof. He's mentioned one proof, a more sophisticated proof you can give using Poitou-Tate and stuff like that. We can give a completely hands-on proof. Well, let me explain briefly, because it's kind of a completely elementary. How do you prove the proposition? For example, I'll prove only the first part. Okay, what one can see, again, just purely by logic, that this exact sequence splits if and only if there exists a certain Kummer extension. So the star QP splits if and only if there exists a certain Kummer extension. So let me call it LQ over this F mu P infinity. So the cyclotomic ZP extension. So this is ZP cross delta. This is Kummer extension. So by this I mean this is a ZP1 extension for the action of this Galois group by by conjugation. Right, so if and only if there exists a Kummer extension with certain properties, for this has to be unramified. So outside Q, outside the primes above Q1, Q2. So for example, in the most delicate condition, if you think about it in an elementary way, is that it's unramified at P and unramified outside Q, and it should be ramified at Q. So I should have just said ramified at Q. And if you just by logic, this is equivalent to this statement. And then one needs to sort of see how do you create such extensions. I mean, if you just use Kummer theory, for example, so you look at F star, and if you look at its p-adic completion, so I'm going to denote elements of F star hat by X hat, and this by Kummer theory is isomorphic to H1 of GF with ZP1 coefficients. Yeah. So now I want to so basically from this one can kind of easily deduce that any extension Kummer extension of this sort is given by basically extracting p to the infinity roots of x hat, right? By this I mean x hat is a sequence of elements, let me call them maybe xn, that is xn is a and of course I mean the obvious thing that by this I mean this is the union of f mu p infinity, maybe let me call this bar, you choose any lift xn of xn bar to f star, and then this is just 1 upon p. That's the obvious thing. Okay, so one wants to do so basically to prove this proposition, all you have to say is what condition on x hat forces this property on the Kummer extension, right? And that's kind of easy to do. So what condition on x hat would make the extension you get by doing the Kummer theory for x hat unramified outside p, unramified at p and ramified only at q1, q2. Okay, so so what is the condition? What is the necessary and sufficient condition on x hat so that it generates? Okay, so it generates this type of extension. Okay, so for each prime q of f, the standard valuation, or whatever it's called, odd, extends to a valuation of f star hat. So if you just had f star, it would be a valuation into z, but as we are looking at hat, it will be a valuation into zp. Right, you have kind of an extension of the valuation from f star to f star hat, and also you have this kind of localization map. So I look at the completion of f at q, and look at his hat again. Right, you have this localization of map. Then the necessary and sufficient condition for, let's say, f mu p infinity x hat 1 upon p infinity to have these properties to be to be unramified at a prime is that the localization map should send x. Okay, first of all, because I want some kind of Kummer extension, I'm going to assume this x hat is a non-Taussian element of f star hat, non-Taussian. It's only then that I get an infinite extension of f mu p infinity. All right. So to be unramified at prime q is that if you look at the localization map applied to x hat, this should be a Taussian element. Okay, now for all primes q different from away from p, this is an unnecessarily fancy way of saying this. I mean, for q not equal to p, this just means that the valuation of q of x hat equal to 0 if and only if, let me call this extension L, if and only if L is unramified at q. Yeah, but for q equal to p, it's, you need to say it this way. So in fact, for q dividing p, for because For q away from p, this completion, basically you kill all the units and so on, and then this just turns out to be isomorphic to zp for q not dividing p. While for q dividing p, it's more intricate. I mean, you get the entire units, right? You get some kind of p-adic manifold of dimension equal to the degree of the local field. Okay, so for p dividing p, of course, I'm assuming the p-th roots of unity are not in the local field, so it's basically the condition that this is 1. All right, so now if you think about it this way, then this proof of this proposition is immediate, more or less. So then we see that the star QP splits if and only if there exists an element x hat, element of f star hat, which in fact, because we want it to be because of this criterion, we want it to be unramified outside P. It is supposed to be in fact, okay, such that valuation of q of x hat is equal to 0 for all q not equal to q1, q2. Valuation of qi of x should not equal to 0. And then this condition that the localization. Okay, so I'm going to also define localization of P to be just the product of the localizations for V dividing P. So localization of P of x hat should be torsion. It's trivial. Right, so now if you the MQs have been designed so that they exactly tell you that MQs, I mean this forces MQ to be finite, the existence of such an element x hat. That's because you can look at the image of this extension. This x hat maps initially to U1 FP, but you can just regard it as an element of E1 EF1 bar. Right, this is some kind of Galois group, or at least. So these conditions basically tell you that this happens. Okay, so you can regard x hat, which is initially here, you can regard it in the smaller quotient. And if you just sort of look at what unraveled definition of Frobenius, or just kind of look at what the Artin symbol means, this happens if and only if there's such an x hat exists. As such, I mean such an exact x hat which satisfies these three properties. Basically, if and only if the Frob Qi satisfy a non-trivial relation. So this will become kind of an exercise. And so this basically just falls out from analyzing Kummer theory a little more. I mean, you have to define these things, and then you get the proof of the proposition for free. The second part, you just have to make everything quantitative, and you get the second part of the proposition, which measures the failure to split over ZP. All right. Okay, so now I mean, but the conjecture for Jacobians was more precise. It was not just something about orders, but actually about the class of the obstruction. So let me just sort of, to finish off this algebraic part of our work, let me just mention that you can make a more precise conjecture. You can make a more precise analog of the formula in the theory of Jacobians. But somehow you cannot work with these compact objects I'm talking about. You have to work with discrete objects. So what one can do is one looks at again the same situation. So an exact analog of the reciprocity, exact analog of the formula alpha PQ So I gave you some kind of numerical evidence of why this MQ kind of plays the role of P minus Q, but you can give something more exact, more kind of more group theoretic, which is rather than just orders, you can identify groups. For that, you look at, again from class field theory, you get kind of an exact sequence. 0 goes to mu p infinity, goes to a infinity q minus, goes to a infinity minus, goes to 0. Now these a infinity minuses, they are what you get by looking at direct limits instead of inverse limits when we made these x infinity minuses. So this is just equal to the direct limit of the a n minus, where this is this, again I remind you, as the Silo P subgroup of the class group of these intermediate cyclotomic extensions. I look at only the minus part, and for this you look at things of you do, instead of class groups, you look at ray class groups of conductor, the primes, the product of the primes above Q in Fn. So this is the Qn is the product of the primes above Q in Fn. You get a ray class group, and because I'm assuming that the number of primes in Q is 2, you get this exact sequence. Okay, now you can harm this sequence. Consider harm of this sequence with a infinity minus, because this kernel is divisible. You get some exact sequence again. I'm looking at linear harms, and then you can then you look at the corresponding long exact sequence of gamma cohomology. So you get something like okay, so you get something like harm a infinity minus into a infinity q minus, and you look at the kind of the connecting homomorphism delta to h1 of gamma with values from harms up between the flanking terms. So harm linear homomorphisms from a infinity minus to mu p infinity, right? And then this Iwasawa pairing is actually a consequence of a more exact pairing which Iwasawa defined, which is he showed that y infinity is equal to linear homomorph as a gamma module, as lambda modules is equal to harm of a infinity minus mu p infinity. And by his theory of adjoints, this kind of stuff is related to x infinity minus, and then you deduce this coarser pairing which I talked about, but actually he proved a more integral version of the pairing. Okay, so anyway, so this is just equal to y infinity, right? And then this is equal to, look at continuous cohomology or whatever, this is equal to y infinity upon gamma minus 1 y infinity. And then the formula one conjectures is, which we think of as an exact analog of this formula, is that if you look at delta of identity, which somehow captures the class of this extension, this is equal to, so if you look at the ZP module spanned by this, it's equal to the cyclic module MQ. So this is this Frobenius module I defined earlier, which is the degree 0 divisors supported on Frobenius of Q1, Q2. All right, so this and one can, again, using kind of this simple-minded Kummer theory, you can certainly prove one version, one case of this conjecture. We don't know how to prove it in general, even assuming Leopoldt or anything. So one can prove a small proposition. One can prove a proposition in the extreme case that if MQ is trivial, then indeed the extension is split. So the conjecture predicts this, but one can prove that, again using Kummer theory and class field theory. All right, so this is how far one can, what we've done about getting a conjecture, getting a criterion, and kind of doing things around it. But how do you prove the criterion? All right, for there we don't really have anything definitive to say, though we've been struggling with the problem for a year or two. Stuck at a certain stage for the last 6-7 months. But let me tell you, what there's a certain tantalizing situation if one tries to think about the proof of the main conjecture of Weil's, and you try to implement those ideas in this context. There's a certain situation you're led to, and we cannot cash in on that situation, but we think it's kind of some interest. All right, so let me tell you, this is much more, this is a rather incomplete part of our work. Okay, so let's kind of switch topics and kind of switch to modular forms. So we were initially, as we started thinking about this because we wanted to understand one of the components of the proof of size conjecture, which is the theorems of Skinner and Weil's on modularity lifting. When we were doing this, we had heard that Fujiwara had an approach to the Leopoldt conjecture using those kind of theorems. So we decided just to understand in a very much, in a probably a more naive way, what the kind of use of auxiliary primes can do in this context. And this is kind of the background of how we started thinking about this. So we were led to this conjecture, and then we were, at some point we were hopeful that this conjecture can be proved using the theory of modular forms. So let me tell you why. Okay, so an approach to the criterion. So this criterion, I mean, I want to prove that this exact sequence star, whatever, QP splits, yeah, for each prime Q, for each pair of primes. Okay, so for this, I mean, what one has to do is one looks at x infinity minus this unramified Iwasawa module, unramified everywhere, and then I localize. So this is a lambda module. So I will localize at the prime of interest, which is the Leopoldt prime ideal. So I localize at the prime of interest, which is I localize at 1 plus t minus u. So I basically localize to the generalized eigenspace for this, for the action of u by 1 plus t, the u generalized eigenspace, right? I'm tensor with QP or something. Okay, and I do the same for this thing I get by adding 2 primes. And basically our thought was that each of these can be constructed using modular forms using the method of Weil's. So what you do is you look at the lambda-adic Hecke algebra of Hida of level Q1, Q2. And so this is the cuspidal Hecke algebra, which is finite over lambda, lambda being the same Iwasawa algebra. And then it kind of injects into the product of T nu, okay, let me call this T. It injects in the product of T nu cross T old, where this nu and old is with respect to the prime Q2. You just choose one prime. So you choose. Okay, so now the techniques of why, I mean, so for first one has to have automorphic constructions of all these objects, which one, for example, Weil doesn't quite construct this automorphically. He constructs most zeros using modular forms, but there are certain zeros like the exceptional zeros and the Leopoldt zeros where he does some kind of limiting arguments and so on. But one has to first try and construct these Iwasawa Galois objects using the T old Hecke algebra. And in fact, one can do this when one adds an auxiliary prime Q1 in this situation, as I'll shortly explain. And then one tries to prove this. So let me call this, for to match with my notation, let me call this T full. Okay. One constructs this Galois module using T full. By construct, I mean via the theory of Eisenstein ideal and so on, which I'll shortly describe in a minute. Yeah, I'll very briefly describe. And then the hope is that, of course, that the T full is splitting, not splitting, but is injecting into the product of two things. So one was hoping that one could at least try to exploit such a situation to produce some kind of splitting as desired by the criterion, right? So of course, something directly certainly that doesn't work, we think, because we've tried and it doesn't work, but it might in the end. But we still think that there is maybe some hope of doing something in the end, though we don't know quite what. All right, so let me kind of fill in what I mean on that board. Okay, so how do you construct this starting with any of these Hecke algebras, T old, T full, or T new? So okay, so if I'm going to just denote any of these Hecke algebras just by the letter T and then elsewhere. Okay, so you just start with any of these 3 Hecke algebras, either the old, the new, or the entire one. And you define a certain Eisenstein ideal. This is a kind of usual Eisenstein ideal which captures the eigenvalues of the lambda-adic Eisenstein series, either of weight 1 or either of level 1 or of level Q1, Q2 stabilized in a certain way. Okay. So you define the Eisenstein ideal by saying what are the elements in it. So one requires the TQ minus 1 minus chi Q norm Q is an element of J for all Q not dividing Q1, Q2P. Maybe I should call this L maybe. Yeah, so you demand this for primes away from the primes of interest, I mean from away from P and Q1, Q2. UP you kind of just impose that UP minus 1 isn't the ideal. And okay, if you're looking, so if I impose this condition for all primes away from P here and this condition for P, then I would get the kind of eigenvalues of the lambdatic Eisenstein series of level 1. But I want to kind of look at its stabilization in level Q1, Q2, and then I stabilize it by imposing the condition that UQI. So I look at the kind of critical specialization of the Eisenstein series. So I look at the eigenvalue I demand is rather than 1, I want this eigenvalue. So I demand that. So I should of course tell you what chi underline is. So chi underline is the universal kind of cyclotomic character. It sends gamma to 1 plus t. That's the kind of universal cyclotomic character. And in the Hira theory, I'm using the normalization that to specialize to weight k. One sends 1 plus t to u to the k minus 2. Okay, so one considers this kind of critical Eisenstein, this Eisenstein ideal. Now, this is an Eisenstein ideal in the full Hecke algebra. So I'll call it J full if I regard it here. And then one can, of course, project it to the old and new. Okay, and then the construction of Ribet Mazur Weils is that basically you look at some kind of lambdatic Galois representation. Initially, it takes place over some kind of fraction field. Choose a lattice and go modulo the Eisenstein ideal, and you get some kind of extension of modules. And this non-semi-simple this extension gives you the modules you're interested in. Okay. So what you do is for any of these T old, T full, T new, you get a Galois representation of the Galois group of F into GL2 of the fraction field of lambda tensor T. And then, okay, I can't explain to you the full construction, but what you do is you choose a lattice inside this kind of thing. You choose some kind of lattice inside the two-dimensional kind of vector space on which this is not two-dimensional module type of thing on which this is acting. So you choose a lattice. And then go modulo JL. Go modulo the Eisenstein ideal. What you get is an exact sequence 0 goes to C, and I apply this for all versions of J, full, old, new. And the Galois action is on GF is by the ident of GF. All these are GF modules. The Galois action here is by the identity, and on here is by a character. Is by the character chi, this underline this kind of universal cyclotomic character times the usual cyclotomic character. It's just the usual CP star valued cyclotomic character. All right, and then if you look at the class of this extension, you choose the lattice in such a way that what you get is that you get a homomorphism from GF or GF infinity rather. So everything is kind of a T mod J module. And you get a kind of homomorphism, a surjective homomorphism from GF more or less after tensoring with QP. You get a surjective homomorphism from GF infinity to C, whose image. So this is kind of some kind of QP vector space. So whose image is of rank the length of J, by which I mean the rank over QP of the appropriate Hecke algebra modulo the appropriate Eisenstein ideal, but localize at the localize. So you localize everything at this Leopoldt prime ideal. So I will explain very roughly what this is. So that is a construction which Weil gives you, and so somehow everything is controlled by the codimension of J inside T. And now how do these J? So one has to look at one has to define certain Eisenstein series which will tell you how deep this is. I mean how large this is. And so you start with the level 1 Eisenstein series. Level 1 Eisenstein series, which would be that Eisenstein series which has eigenvalues these for primes outside P and this for primes at P. So it's kind of some the usual P stabilized kind of Eisenstein series or level P, I should say, not level 1. Okay, so look at the P stabilized Eisenstein series, and now when you look at E minus, let me pretend I'm over Q or something. I mean, look, so it doesn't matter. E of Z minus E Q on Z. So this is the so-called criticalized specialization of the Eisenstein series, because if you look at the other one, there are two possible choices. Either you can look at this, or you can look at something which preserves this eigenvalue while it gives this. But you could look at this, because the point is that once you look at this is indeed congruent to a cusp form, a lambdatic cusp form, modulo 1 plus T minus U, so the Leopoldt ideal, to the M, where M is the required order of vanishing which you wanted to achieve. Where M is the order of this thing which kind of was associated with the zeta function at T plus U, 1 plus T minus U. So somehow the point is that if you work at level outside of level, if you work at level kind of 1 or level P or something, you get 1 less 0 than you want because of the cancellation of some kind of 0 of Wt by some factor. But once you work with a level Q1, when you add level Q1, you restore the kind of 0 you lost, and which the main conjecture predicts you should have. And then when you apply this construction, you get some kind of extension which could possibly be ramified at Q1, but then by a class field theory calculation, you know it's not ramified at Q1, right? So somehow this is a way which Chris Skinner told us was known to him and others, but okay, so it's known to experts, but this is the way to kind of construct this part of the Leopoldt part of the unramified Iwasawa model. So Weil does it by a slightly by a trickier procedure in his paper. All right, so once you've done this, done it here. Once you've constructed the unramified part, you can construct the one with, and then by the main. So you construct a ZP to the M module, where M is this order, which is unramified everywhere. And then after the proof of the main conjecture has been completed, so in the sense using the class number formula, you know that the lower bounds you got are the right bounds and so on. Right, so you get this M, and then when you further stabilize this series at level Q2, I think I'm degenerating into. Okay. Sorry? Yeah, I mean supposed to be 0, yeah, of course, but we want to prove that. Yeah. So you get some series which I'll call EQ1, and then you do the same thing at EQ2, you repeat this construction. What you do is you look at EQ1Z minus EQ1 of Q2Z. Again, I'm kind of pretending I'm over Q in some sense to write such formulas. It may not be a number here, but anyway. So now what I get is that I get an Eisenstein series if you calculate its constant terms, but somehow the interesting constant term doesn't happen at infinity. It happens at the other cusp somehow. I mean, so gamma naught Q has two cusps, right? The standard cusp and the other cusp, and the infinity cusp is just the values, of course, 0, but there are other cusps which detect L values. All right, so this is congruent now to a cusp form modulo 1 plus T minus U to the M plus 1. And now again using the Weil's method, you can construct now some extension which will be of rank at least M plus 1, and which is kind of a which will be ramified only at Q1, Q2, and then by comparing ranks and so on, you see that you constructed X infinity minus Q. Weil's construction gives you from this the construction of X. Okay, so this is the first thing you have to do to implement our strategy. First of all, you have to construct these Galois modules automorphically. But now, okay, so this is kind of the well understood steps more or less. But now, how do you exploit this further? Okay, maybe I'll just take 2 minutes. So in fact, the full and old things have done their job. Now, the only problem is the new part is not doing its job. In the sense, we don't know how to make it construct the extension we want. So the only thing which we have, which we think is a kind of a clue to the situation a little bit, is the following kind of easy observation, but which we think may be useful, is the following fact. The proposition is, and there's again some business of normalization. So now this Leopoldt ideal is going to look slightly different. But J nu, of course, you want us to prove that these are not the entire ring, right? I mean, they're proper ideals. So in fact, J nu is a proper ideal, which you can again do because one has constructed the fully ramified, the full module using the full Heck algebra. So J nu is a proper ideal. Of T nu theta with localization at theta, where theta is this kind of weight zero specialization of the kind of thing which gives rise to weight zero forms when you go modulo that. And in fact, what is more, I mean, this just follows from this construction now, and what is more, and this is a slightly sort of different fact, is that in fact it's a maximal ideal. So I T nu theta upon J nu theta is isomorphic to QP. Right, so therefore the ranks are somehow the Galois situation you want to happen does happen at the level of Eisenstein ideal. So the rank of T full upon J is indeed equal to, and if we localize at the right ideals, localize at all these Leopold zeros, is this ranks do sum up. In fact, this is m plus 1, where m is this kind of hypothetical. M is the order which is supposed to be 0, but we don't know it to be 0. This turns out to be m plus 1. This is m, and this is indeed 1. This m plus 1 and m you get by the proof of the main conjecture. With this 1 you get by a much more elementary and direct computation, using the fact that basically you have to somehow see, you have to compare the relations on the UQ operator imposed by the Eisenstein condition and the newness condition. These conditions are kind of they're kind of transversal to each other, and this is what makes the Eisenstein ideal maximal in the new quotient. So okay, so now I mean this is the situation we are faced with, and what we cannot do is so you can use this proposition and then construct for yourself an extension which you think could be the one you want, but we cannot prove it to be. So using this proposition, you can apply the Weil's method and construct in fact a ZP1 to the something extension. And the advantage of this extension is that because this ideal is maximal, this extension is automatically semi-simple for the gamma action. And it is by construction, by the very nature of the construction, because one chooses the lattice in such a way that this extension does turn out to be unramified everywhere outside, unramified at P, unramified everywhere outside Q1, Q2. Okay, I should finish. But our difficulty is that we do not know how to prove it's ramified at Q. If you could prove by some means that it's ramified at Q, you would get the criterion and you would be done. But again, we think that maybe this is too direct an approach, maybe because we've tried it for a while and it's not worked. But we think that this is a kind of a tantalizing situation where what you want to make happen seems plausible when you think about the construction of these extensions using modular forms. Okay, maybe let's stop here. Sorry for